Welcome back to the e-learning course for Derivatives and Risk Management, Lesson 1, Session 1.3. In Session 1.2, we examined option markets and strategies. In this session, we turn our attention to option valuation issues. To understand most option valuation models requires considerable mathematical and statistical background. However, many of the ideas and insights can be demonstrated in simple examples. We put economic intuition before mathematical rigor. In this session, you will learn basic option valuation techniques. The main goal is to provide you with a basic understanding of the binomial option pricing model as well as the application of the Black-Scholes-Merton formula. Before we talk about option valuation models, we need to get a basic idea what determines option values. Before we do so, we have to clarify some terminology. For that purpose, let us consider a European call option. If the current stock price lies above the exercise price, we say the option is in the money. And when the current stock price is below the exercise price, the option is said to be out of the money. If the stock price equals the exercise price, the option is at the money. The difference between the stock price S and exercise price K is called the intrinsic value of in-the-money call options. The reason for this is it gives the payoff that could be obtained by immediate exercise. For out-of-the-money or at-the-money option, the intrinsic value is 0. The lower bound payoff of a call option when exercised immediately is equal to the difference between the current stock price and the exercise price. This difference is also called intrinsic value. An upper bound can be found by recognizing the fact that the option cannot give a higher ultimate payoff than the stock. If the stock and the option have the same price, everyone will rush to sell the option and buy the stock. Based on these facts, it follows that the option price must be somewhere in the red shaded region. In fact, it will lie on a curved, upward-sloping line like the dash curve shown in the figure. In order to understand this pattern, it is a good idea to look more carefully at the shape and location of the dashed line. In this example, we consider a call option and consider 3 points on the dashed line. In each point, you will see why the option price has to behave as the dashed line predicts. In point A, we recognize that when the stock is worthless, the option is worthless, which leads us to the first important point about option values, which is simply that the value of a call option increases as the stock price increases, if the exercise price is held constant. As you could imagine, this should be no surprise, as owners of a call option hope for the stock price to rise and are happy when it does. The next fact to investigate in greater detail is related to point B, where the stock price has increased substantially and is larger than the exercise price. In such a scenario, there is a high probability that the owner will exercise the option. In fact, we can assume that the stock is effectively owned by the option holder. In these circumstances, buying a call option is equivalent to buying the stock, but financing part of the purchase by borrowing. The amount that is required to borrow corresponds to the present value of the exercise price. The value of the call is therefore equal to the stock price less the present value of the exercise price. Based on these thoughts, it follows that investors who buy stock by way of a call option are buying on credit. They pay the purchase price of the option today, but they do not pay the exercise price until they actually take up the position. The delay in payment is particularly valuable if interest rates are high and the option has a long maturity. Based on these facts, we can conclude that the value of the call option increases with both the rate of interest and the time to maturity. A final statement we can make in terms of the value of a call option is that the value of this option increases with the volatility of the share price and the time to maturity. But how can we justify this statement from an economic point of view? First of all, we have to understand what volatility means. Roughly speaking, the volatility of a stock price is how certain we are about future stock price movements. As volatility increases, the chance that the stock will do very well or very poorly increases. As a holder of a call option, you gain from volatility because the payoffs are not symmetric. If the stock price falls below the exercise price, your call option will be worthless, regardless of whether the shortfall is a few cents or many dollars. On the other hand, for every dollar that the stock price raises above the exercise price, your call will be worth an extra dollar. Therefore, the option holder gains from the increased volatility on the upside, but does not lose on the downside. Finally, note that the difference between the actual call price and the intrinsic value is commonly called the time value of the option. Now let's have a first look at a very simple option valuation model known as the binomial model. For that purpose, we assume that the stock price can take only two possible values at option expiration. The stock will either increase to a given higher price or decrease to a given lower price. Although this may seem an extreme simplification, it allows us to come closer to understanding more complicated and realistic option valuation models. The valuation approach is best illustrated by means of an example where we consider a 6-month call option on a stock with an exercise price of $530. The stock is currently trading at $530, which means the option is at the money. Moreover, the short-term risk-free rate, denoted RF, is 1% for 6 months. Let's further assume that during the 6-month period, the stock price either increases by 25% to $662.5 or decreases by 20% to $424. This implies that at maturity, the option payoff will be $132.5 if the price of the underlying stock did rise, and $0 if the price of the underlying stock did fall. The question to be asked is how can we find the option value in period 0 when the contract is entered? The answer is rather simple and might be surprising on first sight, but will make a lot of sense as soon as you understand the basic idea. The only assumption needed is that arbitrage opportunities do not exist. We set up a portfolio of the stock and the option in such a way that there is no uncertainty about the value of the portfolio at the end of the 6 months. We then argue that because the portfolio has no risk, the return it earns must equal the risk-free interest rate. This enables us to work out the cost of setting up the portfolio and therefore the option's price. Moreover, because there are two securities, the stock and the stock option, and only two possible states, namely a rise or fall in the stock price, it is always possible to set up the riskless portfolio. For that purpose, we buy delta stocks and sell one call option. Based on this insight, we have to calculate the value of delta that makes a portfolio riskless. Now let us take a closer look how to compute delta. In our example, if the stock price moves up from $530 to $662.5, the value of the stock is 530 times delta, and the value of the option is 132.50. So that the total value of the portfolio is 530 delta minus 132.50. However, if the stock price moves down from $530 to $424, the value of the stock is $424 times delta, and the value of the option is 0, so that the total value of the portfolio is $424 times delta. The portfolio is riskless if the value of delta is chosen such that the final value of the portfolio is the same for both states. This means we set the portfolio values in the two states equal to each other and solve for delta. The value for delta, which is commonly called the option delta, is 0.556, which means we have to take a long position in 0.556 stocks and a short position in one call option. Based on this fact, we can compute the value of the portfolio at the end of the life of the option. Regardless of whether the stock price moves up or down, the portfolio value in each state is $235.556. Riskless portfolios must, in the absence of arbitrage opportunities, earn the risk-free rate. In our example, the risk-free rate is 1% for 6 months. It follows that the value of the portfolio today in T0 must be the present value of $235.556. Since the stock price today and the option delta are known, we can solve for the option price C. Doing so shows that the current value of the option must be $61.22. So far, we did study very simple binomial trees consisting of only one period. However, as you know, a stock can usually take on an almost limitless number of future values. The binomial model gives a more realistic and accurate measure of the option price if we could extend the number of sub-periods under consideration. The question that comes with this observation is, how do we pick meaningful numbers for the up and down changes in the stock price? The approach we use here goes back to the late 1970s and was suggested in 1979 by financial economists John Cox, Stephen Ross, and Mark Rubinstein. The basic idea was to choose the up factor U and down factor D in order to match stock market volatility as follows. A formal derivation of these factors is beyond the scope of this introductory course, so we postpone more mathematical rigor for now. In the previous example, we assumed that the stock price would increase by either 25% or decrease by 20% over a 6-month period. Using these numbers to solve the up factor U for sigma, it follows that the volatility consistent with an up factor of 1.25 is 31.56%. When we increase the number of time steps in the binomial model, we must adjust the range of possible up and down changes in the price of the asset to keep the standard deviation constant. As the number of steps increases, the estimated option value would get increasingly close to the Black-Scholes value of the call option. If you have never heard of the famous Black-Scholes option valuation formula before, don't worry, this will be our next topic. A final remark to be made is the following. If you intend to solve a binomial tree with a large number of steps, you need a computer and some programming skills to do so. As you know by now, in each time step, there's a binomial stock price movement. With 26 steps, there are 27 terminal stock prices and more than 67 million stock price paths to be considered. As mentioned before, our next topic in this course is the Black-Scholes option valuation formula. Before we present the formula, we need to introduce one basic assumption. When we increase the number of time steps and generate a larger number of increasingly small sub-periods, it follows that the distribution of price changes becomes increasingly smooth. Based on this, we assume that stock prices S follow a log-normal distribution. This means that the natural logarithm of S is normally distributed. You might recall that returns are defined as the difference of the logarithm of the stock price in 2 consecutive periods and therefore are as well normally distributed. This assumption is very common in financial models and makes a lot of sense, since prices can't be negative, or put it differently, stock prices can never fall by more than 100%. In the early 1970s, Fisher-Black and Myron-Scholes derived a formula to determine the value of stock options. The formula is equivalent to the binomial model if we assume an infinite number of sub-periods. Before we present the formula, let us quickly go through the notation. As before, C denotes the call price, S0 the current stock price, and K the exercise price. R is the risk-free rate, sigma the volatility of the underlying, and T the number of periods to the exercise date. The function n of d denotes the cumulative probability density function for a standardized normal distribution. In other words, it is the probability that the variable with a standard normal distribution will be less than d. The shaded area on the graph on the right-hand side represents n of d. You might find the Black-Scholes formula intimidating on first sight, but we can explain it at a somewhat intuitive level. The basic idea is view the n of d terms as risk-adjusted probabilities that the call option will expire in the money. If we assume both n of d terms are close to 1, which implies a high probability the option will be exercised, then the call option value is equal to the stock price, the present value of the exercise price. However, if the n of d terms are close to 0, meaning that the option almost certainly will not be exercised, then the equation confirms that the call is worth nothing. For values of n of d between 0 and 1, the Black-Scholes formula tells us that the call value can be viewed as present value of the call's potential payoff, adjusting for the probability of in-the-money expiration. Very often it is easier to understand a formula when we consider a specific example. For that purpose, let's assume the stock price and the exercise price are $530, which means the call option is at the money. Moreover, time to maturity is half a year, the annual risk-free rate R is 2.01%, and the volatility is 31.56%. Based on these numbers, we proceed in 3 steps to compute the option value based on the Black-Scholes valuation formula. In step 1, we calculate D1 and D2, which are the input parameters for finding the corresponding values of the standard normal distribution. In a second step, we need to find n of D1 and n of D2. Usually, these values are tabulated and may be found in many statistics textbooks. You can also use the built-in Excel function normDist to get the job done. The final step is to apply the Black-Scholes formula by substituting the corresponding numbers and compute the option value. Doing so for our example implies a call option value of $49.55. You might recall when we introduced the binomial model, we did compute the option delta to figure out how many units of the stock need to be purchased in order to achieve a portfolio payoff that is independent of the state of the world. The economic meaning of the option delta is that it measures the sensitivity of the option value with respect to a unit price change in the underlying. Mathematically, the option delta is the derivative of the call price with respect to the underlying stock price. You can also interpret the option delta as the slope of the curve that relates the option price to the underlying stock price. When doing the computation, the option delta derived from the Black-Scholes model corresponds to n of D1, which means if the price of the underlying asset increases by $1, the price of the call option increases by $0.5622. It is also important to note that the options delta is also known as hedge ratio. In order to hedge the investor's portfolio, for every call option written, 0.5622 units of stock would be needed to hedge the investor's portfolio. For instance, if an investor writes 10 call options and holds 5.622 shares of stock, according to the hedge ratio of 0.5622, a $1 increase in the stock price will result in a gain of $5.622 on the stock holdings. But at the same time, a loss of $0.5622 on each option occurs. Since 10 options have been written, it follows that a loss of $5.622 occurs. In sum, gains and losses from this position are equivalent and the portfolio is thus hedged. After having carefully studied session 1.3, please start with the review questions.